Okay, it seems everything works fine. We are live now. So welcome everyone. Welcome to the next Warsaw University Astronomical Observatory Tuesday seminar series. And today we have an honor to host Professor Tsevi Mazeh from Tel Aviv University. And Tsevi is well-known, renowned planet hunter, but not only planet hunter, he also searches for other interesting phenomena and interesting objects. And Tsevi has been our long-term collaborator since the beginnings of the planetary work here in Warsaw as well. We wish you could visit us here, Tsevi, again in Warsaw, but hopefully next time. But this time, we at least we can have you here through Zoom. So, floor is yours. Please, Tsevi.
All right, thank you very much. And I'm very moved to be virtually in Warsaw. Last time, Simchon and I were at the observatory. It wasn't the first time, but it is great. I'm connected to Poland. My parents came from Poland. I know some words in Polish from my childhood. And in fact, I'm writing a book on Copernicus, which is the Copernican revolution. So it's almost ready. I just do editing, last version editing, and it will come out soon in Hebrew and hopefully will be translated into English. Okay, so thank you for inviting me. And today I want to present a work that I did with Sar Shachaf, who is here as well, and Shai Zucker and Dan Fabriki. And this is analyzing the duration variation of the Kepler transiting planets. So I will start with a long introduction, but the introduction tries to make a point that I think is important. So this is the outline of my talk, and I'll start with a historic introduction. So if we look at the features of the solar system, so first of all, there are many planets in our solar system, 8. The giant planets are far away. They are all in circular orbit. They are all aligned. The planetary orbits are aligned. The obliquity of the star, of the sun, relative to the invariable plane is 6 degrees. And the opening angle of the planets is consistent with a Rayleigh distribution of 2 degrees. So, that led long ago, maybe 200 years ago, something, to the idea that the system was formed from a disk, and the disk had a specific direction, and therefore all the planets adopted this axis of rotation, and therefore all these features. And for many, many years, people assumed that if we find extrasolar planets, they will be similar to this with all these features. Well, as you know, it didn't turn out to be like this. For example, here is the mass period relation for stars that were found by radial velocity, so we know the mass. So this is the mass axis, and this is the period, and you can see that we find many Jovian planets very nearby against this basic feature of the solar system. We also found quite eccentric orbits with planets. Here is one example that Shai Zucker and myself took place in long ago, and by the shape of the radial velocity, you know that this is very eccentric. So 2 of the basic features of the solar system turned out not to be true. Now about the obliquity. The obliquity is defined as the angle between the angular momentum of the planet and the angular momentum of the star, the axis of rotation of the star. And this is, as I said, 6 degrees in the solar system. But it turned out, let's say by the Rossiter-McLaughlin effect, I will not explain this, that some of the planets turned out to be with very misaligned orbit, even retrograde motion, namely that the star is rotating this way and the planet is rotating the other way. So even that is not true. So maybe we have to reconsider the paradigm of the formation, that the formation was not made out of a disk. I don't know, but we have since 95 we have many pieces of evidence that do not work with the basic paradigm. If I may cite Thomas Huxley, that the great tragedy of science is the slaying of a beautiful theory by an ugly fact. So we have to keep our mind open and think, maybe we should reconsider this thing. Anyway, a new era of the extrasolar planets started when Kepler was launched and followed 150,000 stars for 4 years. And between many other things, one of the most important things that Kepler discovered is the multis, that there are many systems that we know now because of Kepler of more than one planet. It's not the only channel of information about the multis, but Kepler is the most important one. So the planetary transit, I don't need to explain this to the people here. The idea is that we observe the light of the star to be diminished periodically by the transit of the planet. And one of the first ones were done in Warsaw. It's a Ogle Transit 56. I collaborated with I had the privilege of collaborating with the Ogle team about this. So that was one of the first groups that produced transits. But Kepler did miracles about this because of the precision and the long time span, the long time span, and the fact that it observed 150,000 stars. So there were many transiting planets found by Kepler, and here is I'm relying on then beautiful figures. Here is this is not updated, but it's almost updated, of the multis of Kepler. You can see every line here is a system. Is a system with some of them with 2 planets, some of them more. And if I may use then a beautiful demonstration of the multis of Kepler. So this is a movie that I hope I will be able to run, and you can see there are many systems here. Each circle here represents a system, and it runs. It is the rate of revolution is correct. I mean, some of them rotate slow and some of them rotate fast, depending, of course, on the radius, on the orbital radius, and there is some music. Again, I hope we'll see that. Right. Okay, so now the challenge of I think of the huge data set of Kepler is to find some features, some statistical features of the multis of the multiple systems that Kepler discovered, and it's not easy, but some people are trying to find the features, and I will try to present to you one specific feature. So, for example, here is I took this figure from He al 2 years ago, and you can see, for example, the number of planets. So there are in Kepler. So there is, for example, there are 253 systems with 2 planets, 100 with 3 planets, and so on. But there is more than 1,000 systems where we know of only 1 planet. So this is a disturbing feature, because, of course, we can say that we see 1 planet with transiting and all the other planets are inclined and therefore we don't see them. Or that they are really single planet systems. Both of these explanations for the singles is a surprise relative to what we think about the solar system and what we think should come out of a formation of a disk, right? So this is the issue, I think. If relative inclination is indeed 1 or 2 degrees, then we should see most of the planets in every system. But the fact that we see that half of them are singles, maybe we have like, this is a make-match, especially Jewish make-match. You know, there are too many singles. So again, this doesn't go. Maybe this is the last feature of the solar system that we find it. It's not. This is not what we see in the many other systems. So how do we go about this? So one, about the statistical features of this. So a few years ago, we constructed a TTV catalog where we analyzed all the transits in Kepler. And for the ones that we have enough signal to noise, we derived the TTV, the time variation, the timing of each individual transit. And we looked for TTVs, and I will show in a minute an example of that. And at that catalog, we also derived for 779 KOIs, the transit durations. If the signal was strong enough, we derived also the duration, and I want to emphasize today about what we can learn from that. That's what I suggest. Anyway, so for example, this is from our catalog of TTVs, of the timing. So you can see, for example, the famous Kepler 9 shows a huge TTV effect, namely that the transit appears earlier or later than you would predict if you assume a strictly periodic motion of the planet. And you can see, for example, that planet number 1 and number 2, they are anti-correlated. The timing, the delay of the happening of the transits are delayed, but by a huge amount. This is 500 minutes. So it's huge. You try to make the timing accurate to maybe a few seconds, maybe a minute, but here it's the delay is huge. And the idea is that these two planets, they are very much near mean resonance, that the period ratio is close, let's say, to 2, and therefore they interact very strongly one onto the other, and one is pushing back the planet, and therefore there is a delay in the transit timing, and the other one is pushed forward, and there is the timing is coming earlier. So this can tell us a lot about the interaction between the two planets, and we showed, and many other people also did that, from that we can estimate the mass of the two planets, because the amount of delay, the amount of disturbance from a Keplerian orbit depends on the mass of the disturber. So this is a huge, rich field that came out of Kepler of analyzing the TTVs. And in fact, it's richer than that. This is a figure from Deck and Egel. So you can see also another effect on top of what I showed you here, the huge, very long delay, or the timing is the transits are coming earlier. There is also another very small but higher frequency, which we call chopping. That this is also, I don't want to go into the details of how it works, but so there is there is a rich information in this timing of the transit, and you can learn a lot about the interaction between them. But what I want to get from this is that there are two time scales of the TTV. One is the relative frequency. This is this one, and one is connected to how close the orbits are close to a resonance. But there is, again, with this Kepler 9, there is another time scale. And you can see that if we measure the duration of the transit, this is the TDV, it's a transit duration variation, you can see that there is a trend here, a linear trend. And this linear trend, it's immediately that it is the time scale is much longer than the Kepler time span. The Kepler time span is fantastic, it's 4 years, but it's not enough. Here you can see, well, we almost caught the whole cycle, maybe a little bit more than that. It's not clear. But here there is some slight modulation on the long term, but the long term is obvious, is part of a much, much longer time scale. And the idea is, and yeah, here is for the other one, the same thing. And the idea is that this transit duration variation is caused by the fact that the impact parameter of the planet is moving. That if, for example, we will start here, and if the impact parameter grows and the chord moves to this place here, then obviously the duration of the transit will change. And obviously, you can immediately ask yourself if maybe the transit will disappear if the if the orbit will move in such a way that the chord will be 0. So here is the idea, and this is the core of my talk. You can imagine that there are 2 planets. One planet here, which is transiting, and there is another planet that we don't see here. We see it in the figure, but in the diagram, but it is not transiting. And because the orbit between these 2 planets is inclined, the 2 orbits are inclined, there is an angle between them, there is a torque on the motion of the transiting planet, and because of the angle, the angle in space of the orbit is changing. So at one specific time, we see the transit here, the transit will be longer. And in another time, because of the precession of the node of the orbit of this planet, it will be here, and that will cause something that the duration will change in this thing here. And the precession cycle is something like 1,000 years, right? So we have only 4 years of data. So in 4 years, right, this is Kepler time span, we just see a trend, a linear trend, but it is a part of a huge, very long cycle. But that's what we have here. It would be better if we can wait for 1,000 years or 2,000 years and then go and analyze it. But the problem is that the time span of a PhD is much less than 1,000 years, so we cannot wait for this. So we have to do the best with what we can. So this is, by the way, a figure from Sarah Milholland that was submitted, and she's analyzing the data in a similar way, and she's coming with a similar conclusion, although a little bit different. Anyway, so the idea of the precession, the idea that we have an eclipsing binary or a transiting planet, and the orbit is not, the inclination is not constant, but it changes, and there is some precession. This is an old idea in eclipsing binaries. This is old. I don't need to tell the senior people in Warsaw about this, and I published, this is my first publication in astrophysics, and so therefore I'm connected to this idea. So this was, we had this idea in '76 that the precession of the nodes in eclipsing binaries can change the orbit because of a third distant companion. And then I did even work with Michel Mayor about this a little bit later. So the idea is very similar. I like to look upon this about as only on the angular momentum vectors. So there is let's say there is one orbit which is orthogonal to this line here, and there is a third companion with a smaller angular momentum, and there is an inclination between them, and this is the total angular momentum. And if we observe the system at a specific time of the precession, that's the angle that we see. And now, if we wait a little bit, they precess, that vector precesses to the other side of the precession, this one, but we don't see this one precess to this one. So therefore, at that, after half precession period, we will see a different inclination. And this is a well-known idea in eclipsing binaries. Here is a citation from the Ogle paper, where they show that some eclipses disappear, like here. These are they are there, but then they disappear, or here they reappear. So all that we know. So this is the idea that we import to the Kepler analysis, and even in Kepler data there is this is not a planet. This is an eclipsing binary, but the eclipsing binary disappears after 2 years or something like this. The eclipse disappears. Okay, so now we come back to the planets. So here is, for example, our analysis of KOI 142. This is the data folded to get the exact shape of the transit, the average shape. This is the residuals, and now we go back and fit this shape to each individual transit, and we measure the timing of each individual transit, and we get this beautiful TTV, transit time variation, and you can see that the period here is quite short. This is like, I don't know, 500 days, 700 days, and this is coming, as I said, from the mean motion resonance of the two planets. So, for example, this KOI, famous KOI 142, many people focused on this very interesting system. At the time, it was not known to have another planet. So we had this indication of a strong interacting planet with the planet that we see only from the TTV. And people also, David Nesvorny and Al, they also did the time duration variation and found that, and analyzed that. So they assumed that the unseen transit has a relative inclination of 2 to 6 degrees, but then there was very recently very nice work by Weiss, and she and with other people, she followed the radial velocity of the unseen planet, and with radial velocity, and she solved it that the relative inclination is 2 degrees. Oh, anyway. And Nesvorny integrated in the computer, of course, how would the duration would look like if we wait enough time. So the conclusion is that after these are two possible solutions, that if we wait 15, 20 years, it will disappear. And if we wait enough, we'll see that in most of the time, the planet KOI 142 will not transit at all, and will come back after in a cycle of 100 days. So you know, all these systems are extremely interesting by themselves, but we try to do, the four of us, is to get some general picture of the system, of the Kepler sample, I would say. Okay, so just a cautious remark. We are interested in the interaction between the planets and the inclination between them, okay? Because you understand that if there is no relative inclination between the planets, there would be no transit duration. If they are all completely fully aligned, there would be no transit duration. There would be a lot of TTV, but no TDV. But we have to be careful because sometimes what we see, and this is a beautiful system, KOI 13, where there is no TTV at all, but there is a very strong TDV. There is a strong change in the duration. And here we know that this is not coming from a adjacent planet, but from the interaction between the quadruple moment of the star and the planet. So when we do notice, or when we do detect the transit duration variation, it's not always coming from another planet. This is something that we have to keep in mind. Of course, this is, and we will see this in a minute, the strength of the interaction with the quadruple moment of the star goes like the radius, the orbital radius to the third power. So this can be seen only for very short planets. All right. So, right. So now we try to do a global picture after all this introduction, but I think it's interesting. So the catalog that we prepared in 5 years ago, and it is in the web, everybody can use it, in 2016, has this catalog has 779 KOIs for which we derived the transit duration for many of them. So now the question is, can we go and do a global analysis of the duration variation and see, and can we learn something from that? Okay, so that's what we did. We analyzed the 561 KOIs, that the signal was large enough and there were 10 transit at least, and we tried to find a linear trend in each of them. So we fit to all of them a linear trend. Of course, you can fit a linear trend to everything, and the question is whether the linear trend is significant. So we assigned a p-value to each of them, and you can see that if we plot the distribution of the p-value, so it is right that it's almost flat, and only there is one bin with a very small p-value, namely significant linear trend. So we believe that this is a strong indication that what we are doing is right. So here is the result, and it was published last week. We have a list. We gave a list of all the analyses, as always. But on top of that, in this new publication, Sar Shachaf is the leading author. We identified 15 KOIs with a highly significant linear trend, and another 16 systems where the significance was intermediate. You can see this is the p-value, and you can see that the duration variation is not much, is on the order of minute per year. So you have let's say an hour of duration, and if you wait a year, you see that the duration changes by 1 minute. Some of them are 6 minutes. Some of them, but that's the order of magnitude that we are talking about. So to do that, you need high precision. You need very good signal to noise. Because what we want to estimate the duration of each specific, each individual transit. So what we do, we fit a global fit to the whole series of transit, and then we go and check whether this template of transit can be changed in the duration in the individual transit. And and then after that we fit all of them, and we see if a straight line is significant. Right, so I want to show you a few examples. I will go very quickly through them. Here is, for example, one example. So you can see that it's quite noisy. Here is the TDV is relative, and then we check by bootstrap and estimate whether this is significant. And for example, for this one, this is what we see, but we do see the timing variation, which is, as I emphasized, this is with a much shorter time scale. There's another one, there's another one, there's another one, there's another one. Each one of them is like a child, you know, we are attached to it, but I will not take your time, you know, to discuss each of them. And right, okay. So now, is there anything that we can say about the whole population? That's the issue, and I'm getting soon to the end of the talk. So right, I saw that. Yeah, so I'll do that. So if you try to write the equations, what do you expect from the duration variation? Assuming there is another planet in the system that exerts torque on the orbit and changes its inclination. So you can write these equations, and then you get this is important. You get the duration derivative. That's what's important. The derivative of the equation. So the derivative is depending on the impact parameter. It depends on the mass of the disturber, M2, and it depends on the period ratio. The planet that we observe is P, and the disturber is with a period of P2. So it's the ratio of the two planets, of the periods of the two planets to the square. And there is an eta, which is just a geometrical factor. And I can give you this is the eta, depends on some inclinations, but it can go up and down through the precession, but it's all on the order of unity. So, okay, so this is the important equation. That's what we expect. So can we check this? So one thing which is very, very important is the relative inclination between the two. As I said, if the relative inclination is 0, there would be no derivative here. So eta will be 0, and therefore the derivative will be 0. But otherwise, if we want to estimate the relative inclination, and this is the core of the discussion, we need to know about the period ratio. And we need to know the mass of the perturber. But we don't know that. In many cases, we don't know what is the period of the other planet. And certainly we don't know the mass unless we do radial velocities from the Kepler data, unless we can do something if the TTV is good enough. So what can we do? So what we can do is to plot our results as a function of the period. Not about the period ratio, because we don't know the period ratio. Not as a function of the mass of the perturber, because we don't know. The only thing we know is the period of the planet. That's the only thing we know. So here we found a surprise, because this is a busy figure. So let me explain. The large dots, these are the significant, the highly significant derivatives. The smaller ones are the intermediate significance. Squares is with when we have we know more than one planet, and all the other ones which are not significant are the gray points here. And here, this is KY13, which we know is coming from the interaction with the quadrupole moment of the star. And this line here is what we expect would be the dependence of the derivative as a function of the period if the derivative, if the TdV is coming from the interaction with the star. Okay, so what we see is that there is a kind of an upper limit here that you can argue, maybe change a little bit the line. We did the best we can. Namely, that there aren't, that's I think clear to me at least, that there are not high derivatives with short period. Let's say here, right? So you can argue maybe it's a selection effect, but this is the selection effect that we could think of, and I will not go into this because I'm running a little bit out of time, but we believe that below that there is no problem with selection effect. So there is a strong, I think, indication that short period planets do not have large duration derivative. That's what it tells me. So maybe it's coming from the fact that for short period binaries, the period ratio is smaller. We don't know what is the period. So let's plot it. So here is a plot of all the known multiple systems. And this is the period ratio between two adjacent planets and the period. There is no correlation. Cannot explain this. Maybe it has to do with the radius, the mass of the other planet, and that may be reflected in the radius. It's a shaky argument a little bit, but there is no correlation with the radius as well. So what can we say? Why is this? And we also checked whether it depends on the radius of the planet, and we don't see anything. So this is the result. There is no short period planet with large duration derivative. Maybe these systems do not have misaligned planetary systems. That's an idea. And maybe for the short period planets, either there was the dissipation at the inner protoplanetary disk that aligned them together, and therefore we don't see high duration, or maybe the other way around, that for the longer periods, there was a dynamical excitation and they opened a little bit the angles. And therefore, we find for the long period, we find high derivatives. So maybe for the larger radii there is a relative high inclination. So again, wow, this is not fitting with the last feature of the solar system. And I want just to comment one more thing. For the long period, if there is a dynamical excitation that opens the angle between the planets, maybe this prevents them from migrating in. So I don't know what is the chicken and what is the egg. So maybe because there is a large inclination, relative inclination, they remained with large periods, or the other way around, because they were left there, they were more susceptible to dynamical excitation and became with large angle. I don't know, but this is an interesting, I think, line of thought. So if there are more systems with relatively high inclination, maybe the singles that we see, they are not singles. You know, it's like you go in the town and you see singles. They are not really singles. They have hidden partners, but they are not transiting, so we don't know about them. That's another thought. Okay, so looking into the future, what can we do in order to improve this figure? The problem is, as I emphasized, that duration changes are slow, of the order of 10 years and some of them 100 years. And Kepler timescale is only 4 years. So we need precise photometry, but long time scale and large sample in order to improve on that. So maybe with Plato, it will be improved. So just to summarize, we produce an easy to use TDV catalog, and we think that there is evidence for systems with short period planets that they are more aligned, maybe, and that maybe indicates either that they were dissipated at small radii, small orbital radii, or that there is a dynamical excitation at large radii. Thank you.
Thank you very much, Tzvi. I do the clapping on behalf of everyone.
Thank you
for this very interesting lecture. Now it's time for questions. If people here on Zoom have a question, then please raise your Zoom hand so that I can see that you want to ask a question. Yes, Ayush.
Hello. That was a nice talk. My question was, I mean, my kind of a concern, like what other phenomena can be, you fear that can be responsible for these changes? As in, because you don't have kind of multi-wavelength photometric studies kind of see if it's kind of, so for example, changing atmosphere opacity of the planet or some other physical phenomena that can, create this.
I don't know, but I tend to think that, for example, the radius, the radius of the planet cannot change this. I'm sorry. It can change the depth, but not the duration. And the depth is very difficult to measure because the depth, we were thinking of this, the depth depends sometimes on background stars. Because the star that you see, if there is a background star and the background star is coming in and out to the pixel of Kepler or TESS or whatever, then it can change the depth that you measure. So the the planetary radius can change, as far as I can see, the depth, but not the duration. The duration is substantially, for 4 years, it's a few minutes. I don't see anything that can do that. And the only thing that changes the orientation of the motion of the planet, either with the interaction of the star, or interaction with another planet.
Okay. But did you rule out any other physical cases that can give such signals?
You can rule out only things that you can think about. Well, maybe there are other things that I cannot think of this, but if I see duration variation, to me it's a strong indication that there is a change in the inclination of the planet, of the orbit of the planet. What can cause this, the thing that I can think about is only, it has to be a torque from outside, either from the star or from another planet. That's what I can think.
Okay, thank you.
Okay, thank you. Any more questions to Tsevi? Milena.
Hello, thank you very much. I have a question, since there were works about comparing TDV and TTV on one plot and trying to figure out the mass. It was in the cases of exomoons. And I don't know, if maybe it was Kepler data or some other data. So does it mean that comparing these two things can give you the mass of the additional body, or?
Yes.
Could you comment?
In many cases, even the TTV by itself, and I also published work on this, can give you some constraints on the mass, or the mass ratio at least between the two. And if you have the TDV as well, it can help you constrain better the mass. And in fact, if you open this door, there was an argument between the radial velocity people and the TTV people, the community, that in some cases the masses coming from the TTV was not consistent with the radial velocity masses, and there was some uneasiness between the two camps. But we published a paper that showed that the TTV is, when it is done right, it can derive the masses correctly. And the advantage is, of course, that this comes free, because you don't need to invest a lot of resources in doing radial velocities. So the answer is, this is a long answer to your question, and the short answer is yes, we can in some cases, not all, in some cases we can derive the masses. But here I'm interested in getting something about the population as a whole and not individual systems.
Thank you.
Okay, thank you. Any more questions? I have a tedious one, of course. Can you use this to find more massive dark bodies, hidden bodies, like neutron stars or black holes in those systems?
In those systems? Wow. Wow, that's an interesting question. My immediate reaction to this, that as I showed, the derivative of the duration or the precession period depends on the mass of the unseen companion. So yes, if there would be a neutron star companion to this, the planet will precess like crazy. In 2 weeks or 3 weeks, it will complete a cycle, and that is difficult to detect because the analysis of Kepler, the basic analysis is taking the whole 4 years and fold it with different periods, as
right,
you know, and find at the beginning, at the starting point, finding the basic period. But let's suppose that this is rotating like crazy, so that then it disappears and comes back, the transit. Can be, and that would be very difficult to take. In fact, I didn't have time, but we do have a case where we have a planet, a KOI number even, that tends to disappear
Mm-hmm.
And it was not found at the beginning. It was found by a planet that did not do this effect, and therefore was found. But we found another planet in the system that was not detected by the pipeline because of the changes. So it would be very difficult to do that. But why do you go to neutron star? Maybe just a star, another nearby star can do the same thing, or say a brown dwarf. It's not as heavy as neutron star. Again, it will induce a very, very high precision. It's a very interesting idea, and one has to write a special pipeline in order to analyze the data and put in the data that the duration is changing.
Mm-hmm.
Otherwise, it will be missed. But it's a very interesting idea.
So there's still more to explore in the data sets. That's great. That keeps us occupied. Yeah.
Thank you. That's a very nice idea.
Okay. Any more questions? I don't see any here, and we're perfectly on time. So let's stop here. Thank you very much, Tzvi, for this very entertaining lecture. And I really loved the animation of the and we could hear the music as well.
That's Dan Fabriki.
Right. Thanks for this. So I'll do the clapping on behalf of everyone. So hopefully next time we'll be able to invite you here in person.
I would love to come. Thank you.
But for now, so thank you all for joining, and see you next week.
Thank you very much. Thank you. Bye-bye.
Thank you.
Thank you. Bye.